So, hi. It's time for us to take a look at quadratic word problems. Don't run away. If they're not that bad, most of them, at least 80% of them, most of the quadratic word problems that we do will follow a very, very similar pattern. And we're going to focus on that pattern in this video, okay? So that when you start to do these, you say, oh, well, that's just that problem again, or that's just that problem again, right? So that you're not scared and upset by it. All right. Now, I want to start this by saying most of the time when we do these problems, our graph looks like this. And we know these 3 points. They're points we've seen a lot in graphing quadratics. This is an x-intercept. This is a y-intercept. And here we've got the x-coordinate of the vertex and the y-coordinate of the vertex. And we know a way to find each of these. If we're finding the y-intercept, we're setting x equal to 0. If I'm looking for an x-intercept, I'm setting y equal to 0. And my vertex, I know the x-coordinate of the vertex is my x equals minus b over 2a. And to find the y-coordinate of the vertex, I have to plug minus b over 2a into all the x's of my parabola. Okay? Most of the time, at least 80% of the word problems that we do involving quadratics, the graph looks like this, and we're looking for one of those 4 things. Now, explicitly, this is usually the picture of a thrown object. So this point here is the initial height. And if this is height as a function of time, then this will be how long until it hits the ground, where the height is 0, right? This is our 0 height line. How long until it hits the ground? This is how long to max height. And this is what is the max height. Okay? And we have a way to find each of these things. If they ask me the initial height, I know I'm finding the y-intercept, so I set x equal to 0. Here, they're asking me to find the x-intercept. I know I set y equal to 0 and solve for x. Here is when does the maximum height occur, and here is what is the maximum height. If I want to know when the maximum height, I use this. And if I want to know what the maximum height is, I do this. And that gets us through most of these problems, okay? Try and take a picture of this. Write this all down. Most of the problems that we deal with will be like this, okay? Now, if you go to our Office 365 assignments channel and look in Files and then look in the folder Polynomials, you'll see in there a worksheet, a PDF called My Wicked Son. True story. This is definitely a true story. I'm going to go through this worksheet with you now. So, one day I was coming back from the mailbox when I heard an evil chortle A chortle is a type of diabolical laugh. All right. Ha ha ha. Moments later, I saw a water balloon headed in my direction, and I noticed my son with a wicked grin on his face, crouching nearby. Being a math magician, I determined his water balloon's path was given by s of t equals negative 16t squared plus 24t, where t is seconds and s is feet. So I'm going to get height in feet when I plug in seconds. Now remember what I said. Most of your pictures will look like this. They'll ask this, the y-intercept is what was the initial height. They'll ask this, the x-intercept, when does it hit the ground? Or they'll ask this, when was the maximum height? Or what is the maximum height? Okay? So let's see what questions they ask me. Okay. Part A. From what height did he throw it? Well, which of these four things is from what height? Did he throw it? Does this x-intercept, when it hit the ground, answer the question from what height did he throw it? No. Does this y value of the vertex tell me from what height he threw it? No. That's what is the maximum height. How about this x-coordinate? Well, it can't be that. That's the time when we get to the maximum height. And this doesn't say when did it reach its maximum height. This says from what height did he throw it. Oh, this point at time equal to 0 is the initial height. From what height he threw it is the same as asking the question, what's the initial height? And how did we find that? If we wanted to find that y-intercept, which in this case is an s-intercept, and that would be a t-intercept, in order to find the s-intercept, we have to plug a 0 in for t. Oops. Negative 16, 24 times 0. And so we end up with 0. Well, so this can't quite be our graph, can it? Because we know at time equal to 0, that was at 0 feet. That was on the ground. So this graph is going to look like that, because we know at time equal to 0, this was on the ground. So that's A. B. What was the balloon's maximum height? Okay, well, we've already found the s-intercept. Is this the maximum height? No. Is this x-coordinate of the vertex, which in this problem is a t-coordinate of the vertex, is this my maximum height? No. This is when do I get to my maximum height. This over here, the y value or s value at that vertex, that's what is the maximum point. And remember, if we're looking for what is the max height, we know that we have to first do x equals minus b over 2a. But in this problem, of course, it's not x, it's t. So my b value is 24, negative 24 over 2 times negative 16. So I have negative 24 over negative 32. I can take an 8 out of each of those, and I get 3/4. So at 3/4 of a second, we'll have the max height, but that's not the max height. This, remember, is the x-coordinate of the vertex. When do we have the max height? We're looking for what is the max height, And remember this notation, f of minus b over 2a, that says that I need to take that answer and plug it into those t's. So let's do that now in order to answer the question, what is the maximum height? S of 3/4 equals negative 16 times 3/4 squared plus 24 times 3/4. Now, you know, a lot of people whimper and complain and want to reach for a calculator, but really 3 squared is 9 and 4 squared is 16. And you don't need to reach for a calculator. And 24 times 3/4, well, those are going to cancel. And so I'm going to get minus 9 plus 18, or 9 feet. So the maximum height is 9 feet. Okay? How did I find that? I realized that the question was asking me to find the y-coordinate, or in this problem, the s-coordinate of the vertex. And in order to do that, I had to find when the maximum height occurred and take that number and plug it into the height function. Okay? And then the last question they ask here is, how long did it take before it hit the ground? Because I wasn't planning on standing there to get hit by it. And so, which of these points is when does it hit the ground? Well, at time equal to 0, it started on the ground, and they threw it into the air, and then it came back down and it hit the ground. So we're looking for this. We're looking for an x-intercept, or in this problem, a t-intercept, because this is the t-axis over here. How do I find that? I set the dependent variable equal to 0. I factor out, how about a negative 8t, leaving me 2 minus 3t. No, 2t minus 3. Yes, that makes sense to me. So that equals 0. Now I've got something times something equals 0. So either 0 equals negative 8t, which means when I divide by negative 8, t equals 0, or 2t minus 3 equals 0. So t equals 3/2, or approximately, or 1.5 seconds. It's going to hit the ground after 1.5 seconds. Better move fast, Mr. Kukla. Okay, I will tell you that it was cold and wet. Next, it says, I ducked behind the side of our house, which is 16 feet tall, to avoid being targeted by more balloons. As a result, James stood up and threw his next balloon from 5 feet. The height of the balloon is now modeled by this new equation. S of t equals negative 16t squared plus 11t plus 5. So at time equal to 0, we see the initial height is 5 feet. He's standing up, he threw from 5 feet, and that's what we've got. Okay, so next it says, would his shot clear the roof? So he threw it from 5 feet, and it's going to go up and come down. And what we want to know is, will it clear the roof? Now we know the roof is 16 feet tall. What I don't know is this 16 feet? In which case, yes, it goes over the roof. Or is this 16 feet? In which case, no, it falls short of the roof and doesn't go over the roof. So how can we figure out whether the balloon will go to 16 feet? Well, most students say that if they knew the y-coordinate of the vertex, if the y-coordinate of the vertex was bigger than 16, then the balloon would go over the roof. And if the y-coordinate of the vertex was below y equals 16, then it would not go over the roof. And so we need to find the y-coordinate of the vertex. And there's a couple of ways, or there's a way we can do that. We did it in the last problem. But before I show that, I do want to say there is another approach to this problem. You pull out your graphing calculator and you graph this. And you do second, calculate, maximum. That's one way to do it, to see what is the vertex here. However, there's yet another way on the calculator we can do it. We'll graph the parabola in y1, and then in y2, we graph the line y equals 16. And then we can actually see, just visually, whether we're getting this line or this line. Okay? But let's do this algebraically, because it's good practice for us. So I want to know the y-coordinate of the vertex. And I know in this problem it's really the s-coordinate. Okay, so I have t equals minus b over 2a. In our problem, that's minus 11 over 2 times negative 16. So I know at 11 over 32 seconds, this water balloon makes its maximum height. So I need to know what s of 11 over 32 is. Is this number going to be bigger than 16 or smaller than 16? So I have negative 16 times 11 over 32 squared plus 11 times 11 over 32 plus 5. Ew, 32 squared? Mr. Kukla, look, I'm sorry, but this is what really happened, and I can't fudge the numbers just to make it easier for you. You wouldn't respect me then for rewriting history. So if I do 11 divided by 32 squared times negative 16 plus 121 divided by 32 plus 5, I end up with 6.891 feet. Well, if that's the maximum height of the balloon, is the balloon going to go over the 16-foot roof? No. So I'm just going to check this with the graphing calculator and look at the graph on the graphing calculator. So I've got here negative 16x squared. Remember, this is negative. That's the subtraction symbol. For this, you want that. Plus 11x plus 5. Now, we think this is a pretty short trip, and we're back on the ground after 1 or 2 seconds, 2. And our height, well, we're wondering about do we get above 16 feet? So I'm going to go to 20 in steps of 2. Okay, and here is y equals 16. Sorry, James. I was safe for the moment. No, this does not go over the roof. Okay. Then, if I didn't duck behind the house, how much time did I have until the balloon would hit me in the chest? Say 5 feet up. Okay, so let's see if we can make sense of this question. We threw it from 5 feet, and we want to know when it gets back to 5 feet. S equals 5 feet. Okay, how much time will we have? Well, there's 2 ways we can do this. We see that this is a point of intersection between the line s equals 5 and our s of t parabola. So we could do 5 equals negative 16t squared plus 11t plus 5. And we can solve this algebraically. Or we could pull out our graphing calculator and graph the line y equals 5. Now, we're not interested in the first time y equals 5. We're interested in the second time y equals 5. And I'm going to change my viewing window to go to y max of 8, because I know I'm only looking for 5. Okay, so that's the point I'm looking for. Second, calculate maximum, and bring my cursor close to that point of maximum. Where are you? Oh, you're way on the negative land. There it is. Close to the point of intersection, and hit enter, and enter, and enter. And so I get that that moment in time was 0.7234 seconds. Okay, well, let's see what happens when we solve this equation. I'm going to subtract 5 from each side. And now I notice I can factor out a negative t from both of these. What will it look like if I factor out a negative t from both of these? Well, 0 equals negative t, 16t minus 11. So I have a thing times a thing equals 0. That means that either this thing is 0 or 16t minus 11 equals 0. When I divide both sides by negative 1, I get t equals 0. So at time equal to 0, the height is 5 feet. And then over here, 16t equals 11, and t equals 11 over 16. So that's 11 over 16. And if I decimalize 11 divided by 16, I get a different number, 0.6875. Well, that's interesting. Makes me want to go back and check my work on the calculator. So here was my graph. Second, calculate, intersect. Did I do maximum before? Yep, because look, 0.6875. 0.6875. Okay. You know, one nice thing about calculator and algebra is that I can use one to check the other. Okay. So, in this problem, they weren't asking about the initial height or when it was on the ground or the maximum height, when the maximum height or what is the maximum height, but they were asking when is this position function equal to 5 feet? And the answer to that was 0.6875 seconds. That's how long I would have to duck behind the house. Go quick, Mr. Kukla. Okay, next. It says, James called a truce with me as he spied some friends coming down the street. But he was feeling tired, and, being a wicked child, he had a wicked idea. He wanted to get on my shoulders to throw balloons from a higher vantage point at his friends. No, really, he did. And so, the new height function for his thrown water balloons is negative 16t squared plus 6t plus 10. Okay? Models the height of the balloon as a function of time. So, balloon. First question. How high is the water balloon when he throws it from my shoulders? Is this when he throws it from my shoulders? No, that's when it hits the ground. Is this when he throws it from my shoulders? No, that's when it gets to its maximum height. Is this when he throws it from my shoulders? Yes. And how do I find this s-intercept? I find an s-intercept by doing s of 0. Negative 16, 0 squared, plus 6 times 0, plus 10. So we know that s of 0 equals 10 feet. Okay, so that's the initial height. That's the height he threw it from my shoulders. Now, what's the next question? How much time does it take the water balloon to hit the ground where his friends are according to this model? Well, this is hitting the ground. And how do we find an x-intercept, or in this problem a t-intercept? That's right, we have to plug the we have to plug 0 into the dependent variable. So how do I solve this equation? Because does it factor? I don't know. I'm going to pull out a negative. 16t squared minus 6t minus 10. Let's see. 16t, t, 10, 1, minus, plus. Did that work? 10t minus 16t is negative 6t. Nice. 10 times negative 1 is negative 10. And don't forget there's a minus out in front. Yeah, that works great. Now, this negative plays no role in determining where these intercepts are, because the first thing I do is divide both sides by negative. That stays 0, and that goes away. So, when are the times when it hits the ground? Well, I see two of them. One of them happens at 16t plus 10 equals 0, where 16t equals negative 10, where t equals negative 10 over 16. Wait a minute, I can't have negative time. That's this over here. That doesn't make any sense in this problem. But I've also got t equals 1 equals, t minus 1 equals 0, where t equals 1 second. So it'll take about a second for that water balloon to reach his friends. And believe it or not, they've actually stayed friends with him all these years. Okay. What's next? His friends, wondering why they might have thought themselves his friends at one time, flee. With no more enemies, I think the matter is over and put James down on the ground again. As I'm standing back up, I notice he's disappeared. And as I walk toward our door, I see that he's climbed on the roof and is in the process of breaking our truce, filled with new energies and evil and wickedness. This is now the model that is used to find the height of the water balloon as a function of time. How high is the balloon when it leaves his hand? Well, what are we talking about here? Is this when it leaves his hand? No. Is this when it leaves his hand? No. Is this when it leaves his hand? Yes. So this is what we're looking for. How do we find this? Well, that's s of 0, which is negative 16, 0 squared plus 24 times 0 plus 16. We know that the initial height, the height at time equal to 0, is 16 feet. And that makes sense because we learned earlier that he was standing on the roof and the roof was 16 feet, that the roof was 16 feet tall. So the water balloon is initially 16 feet tall. Next, what's the maximum height of the balloon and how long does it take to get there? Oh, now we're looking for this. How do we find this point? Well, this is the vertex, and so minus b over 2a will find when is max height. And if I want to know what the maximum height is, I have to plug minus b over 2a into the function. What is max height? Okay, so let's do that. Let's figure this out. So I'm going to have minus b over 2a. And so that's negative 24 over negative 32, or 3/4 of a second. So at time equal to 3/4 of a second, the balloon reaches its maximum height. Now, what is that maximum height? Well, we want to know s of 3/4. So negative 16, 3/4 squared, plus 24 times 3/4, and don't forget the plus 16. This is going to be 9 over 16, and the 16s will cancel, so I'll have minus 9 plus. These can cancel and give me 6 times 3 is 18, but don't forget that, 16 feet. So 9 plus 16, 25 feet. Okay? And if you were checking this on your calculator, you'd type this into Y1, get a good graphing viewing window, and then do second, calculate maximum. Okay, that's part A. No, that's part B. What is the maximum height and when does it get there? After 3/4 of a second. And finally, how much time do I have to get inside before the water balloon hits the ground? Dink, now I'm looking for this. How do I find that point? That's right, that's an x-intercept, or in this problem, a t-intercept. And I find that by setting height equal to 0. Negative 16t squared plus 24t plus 16. Okay, I don't know if it factors, but I do know I can take out a negative 8 from everything. 2t squared minus 3t plus 2. And I wanted to factor that out to make it easier to see if I could factor this trinomial. Let's see. 2t, t, 2, 1. And most people want to do minus minus. However, even though negative times negative is a positive, this is going to be minus 4t minus 1t is minus 5t, not minus 3t. And if I make this one positive to get minus 4 plus 1 for minus 3, now I have positive 1 times negative 2, which is not positive 2. So I'm not going to be able to factor this. Does that mean there's no solution here? Well, there is a solution. I just have to use the quadratic formula. Remember, x equals negative b plus and minus square root b squared minus 4ac all over 2a. Okay, so let's see what we get. We get minus 24 plus and minus square root 24 squared minus 4 times negative 16 times 16 all over 2 times negative 16. Wow, there's a lot going on there, huh? Okay, so I've got 24 squared minus, oops, wrong screen. 24 squared minus a minus is plus. 4 times 16 is 64 times 16. 16 times 64. Okay, so that's going to be 1600. And the square root of that number is 40. And so this is going to be minus 24 plus and minus 40 over negative 32. So one of our answers is minus 24 plus 40 over negative 32. And that's 24 over negative 32. Now that's a negative time. That's this one over here. We don't want that one. We want not the plus version here, but instead we want negative 24 minus 40 over negative 32. So that's going to be negative 64 over negative 32, and that's going to be positive 2. After 2 seconds, this hits the ground. You could, of course, always graph it on your calculator. So we've got negative 16t squared plus 24t plus 16. And we don't need to graph the line y equals 5. But we do need a good viewing window, and we know our maximum height is 25, and I think this is going out to 2, so 2 is going to work, but I probably want to change my y max to be 25. In steps of 2 should be good. So there's my parabola, and I'm looking for this point. When does it hit the ground? I think I want to actually change my viewing window to get a little negative y going here. Negative 5. Not because I think the balloon is going to tear through the ground and go deeper, but instead because I want to be able to find that 0 here, and I want a little space around that x-intercept, or in this case, a t-intercept. Second, calculate 0. Go to the left side of that x-intercept, or t-intercept, and hit enter. Go to the right side of the t-intercept and hit enter. Do you want to guess? No, thank you. And so I end up with 2 seconds. 2 seconds. Okay? So there you go. Now I do say here at the bottom of the worksheet that there are some notes. And those notes are that these equations I was using actually come from Newton's formula for falling objects or thrown objects. He actually created this while he was home from university because the university was closed due to bubonic plague. Maybe one of you will create something like this as well. What we know here is A is the force of gravity. And because gravity brings things down, that's why we have a minus here. Okay? V sub O is the initial velocity. Or how fast does he throw it? And S sub O over here, this is the original or initial height. And we saw that if we plugged in 0 and 0, we'd always be left with this. Okay? So, this is the model we were using, and you'll see a problem like this on the homework worksheet where it gives you this, and then it tells you that I think the helicopter is moving up with a velocity of, I think it's 96 feet per second, and that the initial height when the bale of hay is thrown out is 180 feet. And because we have feet here, our A value, acceleration due to gravity, is 32 feet per second per second. So I'm going to start the problem by plugging these numbers in here. And this is what you'll be doing on tonight's homework worksheet. Negative 1/2 times 32 is negative 16 t squared plus our v sub o plus our s sub o. And so you're going to start this problem by actually building the specific height equation from the information given in the stem of the problem. Okay? Now, I do want to tell you that while we did spend most of this time looking for the same four things, there are some variations that we run into, and it's probably worth talking about. All the problems we did had time here and height here. But sometimes, instead of time, they have x, and that's the horizontal distance away. This is still height, and so when we see this parabola, this isn't how long does it take to hit the ground, but how far is it when it hits the ground. And this isn't how long does it take to get to the maximum height. No, instead this is now going to be how far horizontally from you is it when it gets to its max height. Okay, so same, otherwise, right? It's initial height, it's how far away is it to get to the max height, comma, what is the max height? This is still what is the max height. And this is no longer when does it hit the ground, but how far away is it from you when it hits the ground. And still that's, just a riff on what we've been doing. Now, if you're doing the time version, s of t, negative 16t squared plus 24t plus 16, okay? When we have this situation, we know because of this number, we're talking about acceleration due to gravity being negative 32 feet per second per second. And so my answer when I'm asked, hey, what's the initial height of this object? It's 16, because I put in zeros there. 16 what? 16 feet. But if I see s of t equals negative 4.98 t squared plus 24t plus 16, this number is metric. So negative 9.812 meters per second per second. There's acceleration due to gravity in metric, and so when I multiply that by 1/2, there it is. And so now S of 0 is going to be 16, not feet, but meters. Okay, so if I see this number, I'm in meters. If I see this number, I'm in feet. Okay? Great. Now, there are some quadratic word problems that aren't about throwing objects. So, for example, let's say I have a rectangular garden. Okay? And I've got 96 feet of fencing to enclose this garden. And I'm looking for the dimensions of the garden, which is a rectangle, that maximize area. Okay? The formula for area here I know is length times width. So there's a width, there's a width, there's a length, there's a length. Now, this 96 feet of fencing, that's this, plus this, plus this, plus this. So I could also say 96 equals 2 W's plus 2 L's. Now, what am I supposed to do? Well, I'm supposed to find the dimensions of the garden that maximize area. So maximize is the vertex of a down-pointing parabola. Minimize is the vertex of an up-pointing parabola. So I know when I see maximize area that I want to build an area equation in terms of one variable. It should end up being a parabola with a negative leading coefficient, so I can find the vertex on that parabola. Well, I've got area, but it's not a function of one variable, it's got two variables. I wish I had a helping equation nearby that I could say solve for width or solve for length so that I could get all of this in terms of one variable. And I see right over here a helping equation. If I divide everywhere by 2, I have 48 equals W plus L. And if I subtract L from both sides, I know that W equals 48 minus L. So where I see W over here, I can replace that W with a 48 minus L. So now we've got area equals L times 48 minus L. And if I distribute it, I get negative L squared plus 48L. So now I really do have area in terms of one variable, length, and that's negative L squared plus 48L. Look, it's a down-pointing parabola. So how am I going to find the maximum? Well, I use minus b over 2a, and that's going to be minus 48 over 2 times negative 2, which is 48 over 4, or 12 feet. So my maximum occurs when L equals 12 feet. So this must equal 12 feet. Well, what about these W's? Look, W equals. Oh, well, that's very interesting. W equals 48 minus L. So 48 minus L. We said L was 12. So 48 minus 12 is 36. So this is 36, and this is 36. Excellent. So, can you tell me the dimensions that maximize area? Sure. You should make your rectangular garden 12 by 36 feet. Now, they didn't ask what is the maximum area. You know, I have this area function, this a equals negative L squared plus 48L. And if I graph that, there's 48. That's very interesting. That's 24. What did I think I have to go back and check these numbers. because my max shouldn't be at 12. All right, let's take a look again. So we had said area was length times width. And then we have this helping equation, remember, that said W equals 48 minus L. Okay? So then we have area equals L times 48 minus L. No, I still get 48 there. Oh yeah, I get 48 there. Okay. So, and that's going to be negative L squared plus 48L. Okay. And I graphed it, 0, 48, and halfway between 0 and 48 should be 24, not 12. So let's see what happened here when I set the, when I did minus 48 over 2 times minus 1. Look, I had a 2 in here. Yeah, no. It's minus 48 over minus 2, which is 24. So length is 24, length is 24, and we know W is 48 minus length. So 48 minus 24 is 24 feet. Oh, isn't that interesting? What's the rectangle that maximizes area? Well, I notice all the sides are equal. So we're actually making a square garden. A square garden will maximize this rectangular area. And that's always true, and we'll prove that in calculus. Okay? So they asked what were the dimensions, and now we say 24 by 24 feet. If they had asked what was the maximum area we could get, we could take the dimensions, and we know that area equals length times width. So 576 feet times feet make feet squared. That's our max area. But I also could have found it from the graph at 24. What is this height? So I can calculate maximum. And yet I could also find this by saying, okay, minus b over 2a. And then taking that number, 24, and plugging it into my area function. Remember, the area function was, area as a function of L was negative L squared plus 48L. So that's going to be negative 24 squared plus 48 times 24. And when you add those together, you get the same 576. So you've got ways to do this both with your calculator and algebraically, and you can even see it visually to do this. Notice, I saw the words maximize area. That told me I needed to write an area formula for the rectangle, but I needed to get that area formula in terms of one variable. It doesn't matter if it's L or W. And we had a helping equation, 2W plus 2L, that we used. We solved this for one of the variables. I solved it for W, 48 minus L, and we plugged that in there so we could get area in terms of one letter, L times 48 minus L. Okay? So that's the other type of quadratic that you'll have to see. And you'll see one of those on the homework worksheet. There are a number of problems on the homework worksheet where they give you a parabola equation, plus 10t plus 27, for example. And, oops, X. And maybe the input is the number of dolphins and the output is how many Super Balls. And it's a down-pointing parabola, so there's our graph. And so what's the maximum number of Super Balls and how many dolphins does it take to get there? So we may be given a function that's not a thrown object. Here we have dolphins and Super Balls. And so in a case like this, you're not necessarily going to see the negative 16 or the negative 4.8, 4.9, I'm sorry, that we normally see with the thrown object equations. Okay? I look forward to taking your questions on this, and I'm terribly sorry we're not going to have an opportunity to do catapults. At least that's the way it looks now when I'm making this video, but maybe by the time we get to this, we can do catapults. So let's see. Enjoy the homework, and please do ask questions. It really will help. You might want to go back through these videos if you're not taking notes and take notes on them. It could really help. All right, take care.